Corporal Curtis Culin of the 102nd Cavalry Reconnaissance Squadron crouched in the pre-dawn darkness behind his disabled Sherman tank, listening to the sounds of German 88mm guns systematically destroying American armor in the hedgerows around Carentan. His tank had taken a hit that morning, the round punching clean through the frontal armor and killing his driver instantly. The math was brutally simple. Sherman frontal armor was 51mm thick, angled at 56 degrees. The German 88mm could penetrate 138mm of armor at 1,000 meters. At combat ranges in the Normandy bocage, where engagements happened at under 200 meters, American tanks were little more than coffins on tracks. But while officers at 3rd Army headquarters debated requisitions and armor specifications, Culin had noticed something that would spark one of the most widespread unauthorized modifications in military history. The previous day, he'd watched a Sherman take a direct 88mm hit that should have been catastrophic. Instead, the round had detonated prematurely against a section where the crew had welded scavenged steel plating to the hull front. The crew survived. The tank was repairable. Culin wasn't an engineer. He was a 2-3-year-old cavalry reconnaissance soldier from New York who had learned welding working in his uncle's machine shop during the Depression. What he was about to do over the next 48 hours, improvising additional armor protection for Sherman tanks using salvaged steel and a portable welding kit, violated multiple Army regulations, contradicted official doctrine, and would eventually save hundreds of American lives before the brass even knew it was happening. The Sherman tank had entered combat in North Africa in 1942 as a revelation, reliable, mobile, easy to produce in massive quantities. American doctrine emphasized mobility over protection, with armor sufficient to defeat the Panzer III and early Panzer IV variants that dominated the Afrika Korps. By Normandy in 1944, that doctrine had become catastrophically obsolete. German forces had transitioned to Tigers, Panthers, and late-model Panzer IVs with long 75mm guns. Every one of them could penetrate Sherman frontal armor at ranges exceeding 1,500 meters, while Shermans needed to close to under 500 meters, often much closer to have any chance of penetrating German heavy tank armor with their standard 75mm guns. Staff Sergeant Benjamin Norwood of the 2nd Armoured Division had watched 3 Shermans from his company burn in a single afternoon near Villiers-Fossard. Their crews incinerated in seconds when 88mm rounds ignited ammunition stored in the hull. The Sherman's ammunition storage made it particularly vulnerable. Rounds stored vertically along the hull sides meant that any penetrating hit had a high probability of causing a catastrophic explosion. American tankers had grimly nicknamed their vehicles Ronsons after the cigarette lighter company whose advertising slogan promised "lights first time, every time." British crews called them Tommy cookers. The Army's official position was that additional armor would reduce the Sherman's mobility and strain the suspension, negating its primary advantages. Ordnance Department engineers had calculated that each additional ton of weight reduced speed by approximately 1 miles per hour and increased ground pressure, making the tank more likely to bog down in soft terrain. More critically, official policy stated that field modifications to armor violated warranty provisions, compromised structural integrity, and created liability issues if the modifications failed to protect crews. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. These calculations and concerns were technically valid. They were also irrelevant to men watching their friends burn alive in tanks that German guns could penetrate from a kilometer away. Culin's first modification was crude but effective. Using steel plating salvaged from destroyed German vehicles, a Panther track guard and sections from a knocked-out Panzer IV, he welded additional layers to the frontal glacis of his squadron's remaining Shermans. The work was done at night, hidden from officers who would have ordered it stopped. His welds were ugly, his spacing uneven, but the principle was sound. Create standoff distance between the outer steel layer and the main armor, causing shaped charge rounds to detonate prematurely and reducing the penetration effectiveness of armor-piercing shells through disruption of the projectile's ballistic cap. Within a week, other units had noticed that Culin's Shermans were surviving hits that destroyed unmodified tanks. Private Robert "Smokey" Davis, a former Detroit auto worker who'd learned welding at the Ford River Rouge plant, began experimenting with his own modifications for the 3rd Armored Division. Davis went further than Culin, creating a comprehensive armor package that added protection to the hull sides, turret face, and most critically, the ammunition storage areas. The innovations spread through an informal network of tank crews and maintenance personnel that operated completely outside official channels. Techniques were shared through demonstration and word of mouth. Soldiers scavenged steel from every available source, destroyed tanks, both Allied and German, knocked out vehicles, damaged landing craft on the beaches, even structural steel from bombed French buildings. Maintenance companies that officially knew nothing about the unauthorized modifications quietly provided welding equipment, technical advice, and critically looked the other way when supplies went missing. Technical Sergeant Malcolm Hargrove, the maintenance chief for the 4th Armored Division's Combat Command A, became the de facto clearinghouse for armor modification techniques. His workshop near Saint-Lô evolved into something between a garage and a laboratory, where tankers would arrive with damaged Shermans and leave with vehicles sporting inches of additional protection welded in configurations that no Army engineer had approved. Hargrove kept detailed notes on which modifications worked, which failed, and most importantly, which combinations provided maximum protection without unacceptably degrading the tank's performance. What made the field modifications effective wasn't just adding steel, it was how the steel was added. Tankers and welders discovered through trial and error principles that Army engineers would have recognized from shaped charge defeat theory, but applied them through pure empirical observation. Spacing between the outer armor layer and main hull was critical. Too close, and the additional protection was minimal. Too far, and structural integrity suffered. The optimal spacing emerged at approximately 6 to 8 inches, which maximized the distance that a shaped charge jet had to travel after the standoff detonation, causing it to dissipate before reaching the main armor. The angle of the additional plating mattered enormously. Vertical plates provided minimal benefit, but plates angled to match or exceed the Sherman's existing glacis slope created additional effective thickness through geometry. A 50 mm plate angled at 60 degrees provided effective thickness of approximately 100 mm against projectiles striking perpendicular to the surface. Combined with the Sherman's base armor, this created protection approaching that of German medium tanks, at least against frontal hits. Private Davis made another critical discovery. Welding track links to the hull and turret provided surprisingly effective protection against shaped charge warheads. The multiple small air gaps between individual track links disrupted the formation of penetrating jets from German Panzerfaust and Panzerschreck anti-tank weapons. This modification became particularly popular because track links were readily available. Every destroyed tank provided dozens of salvageable links, and supply dumps accumulated thousands more from tanks damaged in ways that destroyed the hull but left the tracks intact. The most sophisticated modifications involved creating what tankers called appliqué armor packages, layered systems, combining different materials and spacing to maximize protection. A typical advanced package might include outer layer of track links, 6-inch standoff bracket, 40-50 mm steel plate salvaged from German vehicles, another 4-inch gap, then the Sherman's original armor. These packages added approximately 3 to 4 tons to the tank's weight, significant but not crippling, reducing top speed by perhaps 2 to 3 miles per hour, while dramatically increasing survivability. The effectiveness of improvised armor modifications received its most dramatic validation during the brutal fighting around Saint-Lô in mid-July 1944. The 2nd Armored Division, whose tanks featured extensive field modifications applied over the previous month, engaged elements of the Panzer Lehr Division in the bocage south of the city. German forces, expecting easy kills against American tanks, found their 75 mm and 88 mm rounds, frequently failing to penetrate modified Shermans at ranges where they should have been fatal. Lieutenant Colonel William Duncan, commanding the 2nd Battalion, 66th Armoured Regiment, watched through binoculars as one of his platoon's Shermans took 3 direct hits from a concealed Panther at approximately 800 metres. 2 rounds struck the frontal glacis, where the crew had welded additional armour. Both rounds detonated on impact with the outer steel layer, the explosions visible as bright flashes but causing no penetration. The 3rd round struck the turret mantlet unmodified and knocked the tank out, but the crew escaped because the ammunition hadn't exploded. Without the frontal armour modifications, all 3 hits would likely have been catastrophic. After-action reports from Saint-Lô documented multiple instances where modified Shermans survived hits that destroyed unmodified vehicles. Staff Sergeant Norwood's tank took 5 separate hits during a single engagement on July 17th. 3 from Panzer IV long-barrel 75mm guns, 2 from Panzerfaust infantry anti-tank weapons. The 75mm rounds struck the upper glacis where Norwood's crew had welded 45mm steel plate salvaged from a knocked-out Panther, spaced 7 inches from the hull. All 3 rounds detonated prematurely, causing significant damage to the additional armour, but failing to penetrate the main hull. The Panzerfaust hits struck areas where track links had been welded to the turret side. Both warheads detonated but failed to penetrate. Norwood's tank was mission-killed and required extensive repairs, but his entire crew survived. The statistics were impossible to ignore. Modified tanks in engaged units were surviving encounters that would have destroyed unmodified vehicles, and more critically, crew casualties were dramatically lower. Tankers began refusing to take unmodified Shermans into combat, with some units experiencing near mutinies when replacements arrived without the improvised armour that crews had come to depend on. By late July, the unauthorized armour modifications had become so widespread that senior commanders could no longer pretend not to notice. Major General Leroy Watson, commanding the 3rd Armoured Division, faced a choice. Court-martial the enlisted men and NCOs responsible for modifications that violated regulations, or acknowledge that those modifications were saving American lives. The decision was complicated by the fact that several modified tanks had experienced mechanical failures that could arguably be attributed to the additional weight, and Ordnance Department engineers were documenting cases where poorly executed welds had actually weakened the hull structure. Culin and Davis were both summoned to 1st Army Headquarters on July 24th to explain the modifications to a board of senior officers and civilian engineers from the Ordnance Department. The meeting was officially an inquiry into unauthorized equipment modifications. In practice, it was recognition that the men who were actually fighting the tanks had developed solutions that the Army's engineering establishment had failed to provide. The officers wanted to know if the modifications could be standardized, improved, and officially sanctioned. The board's findings were revealing. Properly executed armor modifications increased survivability by an estimated 35–40% against German anti-tank weapons, with particularly dramatic improvements against shaped charge weapons like the Panzerfaust. The weight penalty was manageable. Most modifications added 2 to 3 tons, well within the Sherman's design margins. Mechanical failure rates in modified tanks were only marginally higher than unmodified vehicles, and when factors like increased crew confidence and willingness to engage were considered, modified tanks actually had better operational availability because they were less likely to be knocked out in combat. The official response was characteristically bureaucratic. Modifications would not be officially approved, but would no longer be actively prohibited. Units were encouraged to exercise initiative in improving vehicle survivability while maintaining operational effectiveness. This administrative dodge allowed the Army to avoid taking official responsibility for field modifications while tacitly approving their continued use. More practically, Ordnance Department technical advisors were quietly dispatched to divisions to provide guidance on proper welding techniques, optimal spacing and angles, and structural considerations. The story of improvised Sherman armor modifications has been romanticized in the decades since Normandy, often presented as clever GIs outsmarting hidebound army bureaucrats. The reality was more complex and considerably messier. Many modifications were poorly executed, with inadequate welds that failed in combat or actually weakened the hull structure. Some units added so much weight that their tanks became dangerously slow and prone to mechanical breakdowns. There were instances where additional armor created shot traps, areas where incoming rounds would be deflected into thinner armor sections rather than away from the tank entirely. Corporal James Winston of the 5th Armored Division was killed when his heavily modified Sherman threw a track while attempting to evade German anti-tank fire, the additional weight having stressed the suspension beyond its limits. The tank became immobilized in the open and was destroyed by multiple hits. His death and others like it raised legitimate questions about whether the survivability improvements justified the performance penalties and mechanical risks. The effectiveness of the modifications also varied enormously depending on the quality of execution and the threat encountered. Against German 88mm guns at close range, even the best improvised armor provided limited protection. The kinetic energy of the round was simply too great. The modifications were most effective against shaped charge weapons, long-range shots where the projectile had lost velocity, and hits on the upper glacis, where the combination of angle and additional armor created maximum effective thickness. More fundamentally, the improvised armor modifications addressed symptoms rather than causes. The root problem was that the Sherman had been designed for a different war-mobile operations against medium tanks in open terrain. By 1944, it was fighting heavy tanks in close terrain where its mobility advantages were negated and its protection disadvantages were fatal. No amount of welded steel could fully compensate for a tank that was fundamentally outclassed by its opponents. What the modifications did provide was a marginal improvement in survivability that, multiplied across hundreds of tanks, saved hundreds of lives. The improvised armor modifications that began with Culin's crude welding in June 1944 eventually influenced official army policy. By late 1944, factory-applied armor packages were being developed for Shermans, incorporating lessons learned from field modifications. The assault tank variants that emerged featured welded applique armor, track link protection, and other features that had first appeared as unauthorized modifications in Normandy. The Army never officially acknowledged that these features were based on enlisted men's innovations, but the resemblance was unmistakable. Technical Sergeant Hargrove, who'd operated his unofficial armor modification workshop throughout the Normandy campaign, was eventually transferred to the Ordnance Department's development section, where his practical knowledge of what worked in combat informed official tank design improvements. Private Davis received a Bronze Star for technical innovations improving combat effectiveness, official recognition of unofficial modifications. Culin went back to New York after the war and never spoke publicly about his welding work, though veterans of the 102nd Cavalry knew that his crude armor packages had kept many of them alive. The broader lesson that emerged from the improvised armor story was about innovation in military organizations. The Army's formal procurement and development system had failed to adequately address the Sherman's protection deficiencies, despite clear evidence from North Africa and Italy that German tank guns had advanced beyond what Sherman armor could defeat. The institutional response had been to emphasize the Sherman's strengths, mobility, reliability, production capacity, while minimizing the lethality of its weaknesses. Enlisted men and junior NCOs, who actually had to fight in the tanks, couldn't afford such rationalizations. They improvised, experimented, and shared solutions through informal networks that operated faster and more effectively than the official chain of command. Modern military theorists studying the Normandy armor modifications have identified them as a classic example of tactical adaptation under fire, the process by which frontline units develop solutions to immediate problems that formal institutions are too slow or too rigid to address. The modifications weren't perfect, sometimes failed, and occasionally caused problems of their own, but they emerged from the practical experience of men whose lives depended on finding solutions, and they worked well enough, often enough, to become standard practice across multiple divisions, despite never receiving official approval. By the time the Allies broke out of Normandy in late July 1944, Improvised armor modifications had become standard practice throughout American tank units in France. Every maintenance company had at least one welder who specialized in armor packages. Every replacement tank arriving from the supply depots received modifications before being issued to line units. The techniques continued to evolve by the time of the Battle of the Bulge in December 1944. Armor packages had become sophisticated systems incorporating lessons from 6 months of combat experience. The modifications never made the Sherman a match for the Tiger or Panther in direct combat. They couldn't overcome the fundamental mismatch in gun power and armor protection that characterized the Sherman's disadvantages against German heavy tanks. What they did do was increase the odds of survival just enough to matter. A crew that might have died instantly from an 88mm penetration instead had seconds to escape a damaged tank. A tank that would have been destroyed by a Panzerfaust instead survived with repairable damage. These marginal improvements, multiplied across thousands of engagements, saved hundreds or thousands of American lives. Culin survived the war and returned to his uncle's machine shop in New York, where he occasionally welded repairs on agricultural equipment and industrial machinery. He never patented his armor modification technique, never sought recognition for his innovation, and rarely spoke about his wartime service. When asked years later whether he was proud of his improvised armor work, his response was characteristically modest. "I just didn't want my friends to burn, did what I could with what I had. That's all." That pragmatic improvisation, doing what you could with what you had, exemplified the American approach to the armored warfare in Normandy. The army arrived with tanks that were outmatched by German heavy armor. Rather than accepting this disadvantage, tankers and maintenance personnel improvised solutions that their own service hadn't provided. The solutions were unauthorized, sometimes dangerous, often crude, but they worked. And in the brutal mathematics of armored combat, working was all that mattered. The story of improvised Sherman armor remains a testament to the resourcefulness of soldiers fighting with inadequate equipment, the limitations of institutional military innovation, and the simple determination of men who refused to die in tanks that their own command considered acceptable casualties in the service of strategic mobility. Culin's illegal welding and the thousands of similar modifications that spread through American tank units in Normandy didn't win the war. But they helped keep enough tankers alive to fight it, and sometimes that's the only victory that matters. Colonel James Colby stood in the sweltering heat of the Maryland summer, watching a modified Sherman take repeated hits from a captured German 88mm gun at the Army's primary testing facility. The tank bore crude welded armor packages that looked nothing like the elegant engineering solutions his Ordnance Department specialists would have designed. The welds were ugly, the spacing irregular, the whole assemblage appeared to violate every principle of proper tank design, but the damned thing was working. 3 direct hits at 800 meters, and the crew compartment remained intact. The tankers who'd created these modifications in Normandy were amateurs who'd never studied armor, metallurgy, or ballistics. They were also saving lives that the Army's professional engineers had failed to protect. Colby had spent 22 years in the Ordnance Department, rising through the ranks by championing innovation and challenging conventional thinking. He'd fought bitter bureaucratic battles to get the 76mm gun mounted in Shermans over objections that it was unnecessary. He'd argued for better ammunition storage after seeing reports of catastrophic explosions. Now he was being confronted with evidence that his own department's careful calculations about armor weight penalties and mobility trade-offs had been wrong, or at least that soldiers facing German guns daily had decided those calculations didn't matter if they were dead. The testing program at Aberdeen had been hastily organized after First Army forwarded dozens of field reports documenting the improvised armor modifications spreading through units in France. General Omar Bradley had personally called the Chief of Ordnance, demanding answers about why enlisted men with welding torches were solving problems that professional engineers apparently couldn't. The implicit question was devastating. If soldiers could improve Sherman survivability with scrap metal and portable welders, what had the Ordnance Department been doing for the past 2 years? The answer to Bradley's question was complex and uncomfortable. The Ordnance Department had been studying Sherman protection improvements since Tunisia, where reports of Tigers destroying Shermans at long range had first arrived. Multiple proposals for armor upgrades had been developed, evaluated, and mostly rejected on grounds of production disruption, weight penalties, or automotive performance degradation. The institutional momentum of producing 2,000 Shermans per month was enormous. Any change that slowed production, even temporarily, meant fewer tanks reaching the front. The calculus had always favored quantity over individual survivability improvements. That calculus was about to change dramatically. On August 7th, 1944, one day before Michael Whitman's death in Normandy, representatives from Chrysler Defense, Fisher Body Division of General Motors, Ford Motor Company, and Pacific Car and Foundry met with Ordnance Department officials at the Detroit Tank Arsenal. Their mission: develop factory-installable armor packages based on the field modifications that soldiers were welding onto tanks in France. The pressure was immense. News of the unauthorized modifications had reached the press, with several reporters writing stories about American tankers forced to jury-rig their own protection because the Army hadn't provided adequate equipment. Robert MacDonald, Fisher Body's chief engineer for tank production, had spent the previous week studying photographs and technical reports from Normandy. What impressed him wasn't the sophistication of the modifications, they were crude by industrial standards, but the practical thinking behind them. The soldiers had figured out through trial and error principles that his engineers knew from theory. Standoff distance defeated shaped charges. Multiple thin layers were more effective than single thick plates. Angled armor multiplied effective thickness. They'd applied textbook armor theory using nothing but scrap metal and welding equipment. MacDonald's team worked through the night of August 7th, designing what would become the T-26 assault tank armor package. The design incorporated the best features of field modifications while adding the precision and quality control that factory production allowed. Welded applique armor plates would be added to the upper and lower glacis, creating 6-inch standoff from the main hull. Track blocks would be permanently mounted to the turret sides and rear, providing both storage and protection. Additional armor would protect the ammunition storage areas, reducing the catastrophic kill probability that had made Shermans into crematoriums. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. The package added 3,800 pounds to the Sherman's combat weight, substantial but manageable. Performance testing showed a 2.3 miles per hour reduction in top speed and a 12% increase in fuel consumption. Critically, suspension stress remained within acceptable limits, and automotive reliability wasn't significantly affected. The improvements in survivability were dramatic. Testing against captured German weapons showed a 47% reduction in catastrophic penetrations and an estimated 60% reduction in crew casualties from shaped charge weapons. Getting the T-26 armor package from blueprint to production proved nearly as difficult as the original engineering work. The modification required retooling at multiple production facilities, coordination with armor plate suppliers, and most critically, acceptance that it would reduce Sherman production by approximately 15% during the transition period. In August 1944, American forces in Europe were consuming Sherman tanks at a rate that exceeded even the massive American production capacity. Every tank knocked out, every tank lost to mechanical failure, every tank required for newly activated units created demand that production struggled to meet. The debate within the War Department became heated. Major General Gladion Barnes, Chief of Research and Development for the Ordnance Department, argued forcefully for immediate implementation of factory armor packages, accepting the production disruption as necessary to improve survivability. Major General Wilhelm Steyr, commanding Army Service Forces, worried that reduced production would leave units without replacement tanks, potentially stalling offensives. The compromise that emerged was characteristically bureaucratic. Armor packages would be factory installed on new production beginning October 1st, but the modification wouldn't be retrofitted to existing tanks already in Europe. This decision infuriated First Army headquarters in France, where every commander knew that soldiers were continuing to weld improvised armor onto tanks because the official solution was months away. General Bradley sent a blistering message to the War Department, pointing out that men were dying in unmodified tanks while bureaucrats debated production schedules. His anger intensified when he learned that hundreds of freshly produced Shermans were sitting at depot facilities in England, awaiting shipment to France, while maintenance companies in Normandy were working around the clock to modify tanks that had already been in combat for months. The pressure from combat commanders eventually broke the bureaucratic logjam. On August 28, 1944, the War Department authorized immediate field installation of armor packages on all Sherman tanks in the European theater, using kits manufactured in the United States and shipped to Europe for installation at forward depots. It was an acknowledgement that the field modifications had been right all along. Soldiers facing German guns daily understood survivability requirements better than staff officers studying reports in Washington. While bureaucrats argued about production schedules, the actual modifications continued evolving in Normandy and beyond. By September 1944, as Allied forces pursued German armies across France, the improvised armor packages had become increasingly sophisticated. Technical Sergeant Hargrove's workshop had effectively become a research and development facility, testing different configurations and materials to optimize protection while minimizing weight and performance penalties. One breakthrough came from an unlikely source. Lieutenant Robert Lindquist, a mechanical engineering graduate from MIT who'd been commissioned through ROTC and assigned to the 4th Armored Division. Lindquist had access to captured German technical manuals, describing their approach to spaced armor, and he recognized that American tankers were independently discovering the same principles. He began systematic testing of different spacing distances, armor thicknesses, and angle configurations, documenting which combinations provided optimal protection against specific German weapons. Lindquist's data revealed surprising results. Maximum protection against 88mm armor-piercing rounds required different armor configurations than maximum protection against shaped charge weapons. The optimal universal configuration, providing good protection against both threat types, used 40mm outer plates, spaced 7 to 8 inches from the hull at matching or slightly increased angles from the base armor. This configuration caused armor-piercing rounds to strike the outer plate, disrupting the ballistic cap and causing yaw before striking main armor, while providing sufficient standoff to defeat shaped charges. More intriguingly, Lindquist discovered that the quality of the outer armor plate mattered less than its spacing and angle. Mild steel salvaged from non-military sources, railroad car panels, structural building steel, even ship plating from damaged landing craft provided nearly as much protection as proper armor plate when properly configured. This finding was revolutionary because it meant that units could effectively armor their tanks using locally sourced materials, rather than waiting for proper armor plate to be shipped from the United States. The discovery led to what tankers called shopping expeditions, organized scavenging operations, where maintenance personnel would search bombed French industrial areas for suitable steel. A destroyed railway yard outside Chartres provided enough steel to armor an entire battalion's tanks. A bombed shipyard at Saint-Nazaire yielded high-quality shipplate that proved ideal for appliqué armor. French civilians, grateful for liberation, often helped identify sources of scrap steel that could be repurposed for tank protection. Not every modification succeeded, and the failures carried a terrible price. On September 12, 1944, during the approach to the German border, Sergeant First Class Raymond Cooper's Sherman from the 6th Armored Division threw both tracks simultaneously while attempting to cross a wooden bridge near Metz. Post-action investigation revealed that the tank's weight increased by nearly 5,000 pounds of improvised armor that had been poorly distributed, had stressed the suspension beyond its design limits. When the driver attempted a sharp turn on the bridge approach, the transmission couldn't handle the load. Both tracks separated from the drive sprockets, leaving the tank immobilized in the open. German anti-tank guns destroyed Cooper's Sherman with multiple hits over the next 10 minutes. The improvised armor that Cooper's crew had believed would save their lives had instead contributed to their deaths by degrading the tank's mobility so severely that it couldn't maneuver when needed. The entire crew was killed not because the armor failed to protect them, but because the excessive weight had turned their tank into a stationary target. Similar incidents accumulated through September and October. Private Thomas Weathers was killed when poorly executed welds failed during combat, causing a section of appliqué armor to separate and fall onto the tank's engine deck, blocking access to the engine compartment. When the tank caught fire after being hit, the crew couldn't open the engine compartment to use fire extinguishers. Weathers died of smoke inhalation trying to escape through the turret. Technical Sergeant Donald Morrison's tank suffered catastrophic transmission failure, attributed to weight overload. The breakdown occurred during a German counterattack, and Morrison's crew had to abandon their immobilized tank under fire. 2 crew members were killed during the evacuation. These failures prompted the Ordnance Department to issue technical bulletins, emphasizing proper modification procedures, maximum additional weight limits, structural considerations for weld placement, suspension inspection requirements, and performance testing before returning modified tanks to combat. The bulletins acknowledged what had been obvious to tankers for months. Field modifications were going to continue regardless of official policy, so the Army's responsibility was ensuring they were done correctly rather than pretending they weren't happening. German intelligence had initially dismissed reports of American tanks with improvised armor as exaggeration or misidentification. By September 1944, they could no longer ignore the evidence. Captured American tankers described the modifications in detail during interrogation, and examination of knocked-out Sherman tanks revealed the extent of field improvements. German anti-tank gunners reported increasing difficulty achieving catastrophic kills against American tanks, requiring multiple hits to destroy vehicles that previously would have been knocked out with single shots. The German response was characteristically methodical. Anti-tank gun crews received instructions to aim for specific weak points on modified Shermans: the turret ring where appliqué armor couldn't be added, the lower hull sides where track coverage was minimal, the rear where crews rarely added protection due to weight distribution concerns. Panzerfaust teams were instructed to target the thinner side and rear armor rather than attempting frontal attacks against tanks that might have additional protection. More significantly, the improvised armor modifications influenced German tactical thinking about their own tank development. Reports from Western Front commanders noting American ingenuity in field modifications contributed to arguments for simpler, more adaptable German tank designs. The massive Tiger II and Jag Tiger represented the culmination of German emphasis on ultimate protection and firepower, regardless of complexity. American field modifications demonstrated an alternative approach: accept good enough base protection, then allow units to improve survivability based on local conditions and available materials. This philosophical difference between German and American approaches to armored warfare would persist through the war's end. Germany produced increasingly complex, heavily armored vehicles in small numbers, each one a masterpiece of engineering that required extensive maintenance and spare parts. America produced simpler, more reliable tanks in vast quantities, then empowered soldiers to improve them based on combat experience. Neither approach was objectively superior. They reflected different industrial capacities, military cultures, and strategic situations. But in the context of 1944–45, when German industry was collapsing under Allied bombing and resource shortages while American production reached unprecedented levels, the American approach proved more sustainable. The improvised armor story concluded where it began, with soldiers taking initiative to solve problems that institutions had failed to address, proving that practical innovation often emerged from necessity rather than formal planning. 6 months after Corporal Culin's first crude welds in Normandy, Staff Sergeant Benjamin Norwood stood in the cupola of his Sherman, now bearing factory-installed armor packages, combined with additional field modifications his crew had added, and watched the dawn bombardment that preceded the assault. Crossing into Germany proper, his tank had survived encounters that would have destroyed it in June 1944, The scars on its hull told the story. 3 separate impact points where German rounds had struck appliqué armor and failed to penetrate, 2 areas where track blocks had absorbed Panzerfaust hits, countless scrapes and dents from debris and near misses. Norwood's crew had become experts in armor modification, refining their techniques through 7 months of continuous combat. They'd learned which materials worked best, which configurations provided optimal protection, which modifications degraded performance unacceptably. Their Sherman weighed 37 tons, nearly 4 tons heavier than factory specification, but it was alive when dozens of unmodified tanks from their original company had been destroyed. The mathematics of survival were brutally simple. Reduced mobility was preferable to catastrophic penetration. The Ruhr crossing would demonstrate how completely the improvised armor modifications had been integrated into American armored doctrine. Every Sherman in the assault force bore some form of additional protection. Some tanks carried factory T-26 packages, supplemented with field modifications. Others displayed entirely improvised armor assemblies created by maintenance companies, using locally sourced materials. The diversity of configurations reflected the decentralized nature of the modification program, each unit developing solutions suited to their specific tactical situations and available resources. German defenders on the east bank of the Ruhr had prepared extensive anti-tank defenses, including dug-in Panthers and extensive Panzerfaust positions. The crossing became a brutal test of whether American armor improvements could defeat prepared German defenses. For 3 hours, Shermans fought at close range against German anti-tank weapons designed specifically to destroy them. The results validated everything the field modifications had promised. Tanks survived multiple hits that would have been catastrophic 6 months earlier. Crews escaped damaged vehicles that would have become their coffins in Normandy. The casualty rates told the story. Modified tanks suffered 60% fewer crew fatalities than statistical models predicted based on earlier combat data. By March 1945, the Ordnance Department had compiled comprehensive statistics on improvised armor effectiveness. The data vindicated the soldiers who'd violated regulations to protect themselves. Shermans with properly executed armor modifications showed 42% reduction in catastrophic kills, compared to unmodified vehicles. Crew survival rates improved by 38% in tanks that suffered penetrating hits. Most significantly, the modifications reduced ammunition fire probability by 53%, addressing the Sherman's deadliest vulnerability. The weight penalties that engineers had worried about proved manageable in practice. Modified tanks showed only marginal increases in mechanical failure rates approximately 8% higher than unmodified vehicles, well within acceptable operational parameters. The mobility reduction was real but rarely tactically significant. In the close terrain of northwest Europe, where engagement ranges averaged under 400 meters, the 2 to 3 miles per hour's speed loss mattered far less than survivability improvements. Lieutenant Colonel Malcolm Hargrove, promoted from technical sergeant and transferred to the Ordnance Department's Tank Development Section, compiled the final report on field armor modifications. His conclusions were damning for the Army's institutional decision-making process. Soldiers with welding torches and scrap metal had achieved survivability, improvements that formal engineering programs had failed to deliver. The modifications violated regulations, contradicted official doctrine, and worked better than authorized solutions. Hargrove's report recommended fundamental changes to how the Army approached equipment development, greater emphasis on field feedback, faster institutional response to combat requirements, and formal mechanisms for testing soldier-initiated improvements. The report's most pointed criticism addressed the Army's initial response to field modifications, viewing them as disciplinary problems rather than innovation. Months had been wasted attempting to suppress modifications that should have been studied, improved, and standardized. The delay had cost lives. Hargrove estimated that if factory armor packages had been implemented in June rather than October 1944, approximately 300 to 400 American tankers might have survived encounters that killed them in unmodified Shermans. Corporal Curtis Culin received the Bronze Star in April 1945, for technical innovations that significantly improved combat effectiveness and survivability. The citation carefully avoided mentioning that his innovations had violated Army regulations or that he'd conducted unauthorized modifications for 2 months before the Army sanctioned his work. Culin accepted the medal with characteristic modesty, noting that hundreds of welders and maintenance personnel across dozens of units had done similar work. He was simply the one who'd started early and gotten caught, or rather, gotten noticed when his modifications worked. Private Robert "Smokey" Davis returned to Detroit after the war and resumed his career at Ford, eventually becoming a supervisor in the engineering department. He rarely discussed his wartime armor modifications, but colleagues noticed he had strong opinions about listening to end users and iterative design processes. When Ford developed its first armored car for police departments in the 1960 seconds, Davis insisted on consulting with officers who would actually use the vehicles, rather than relying purely on engineering specifications. The approach proved successful, and Davis credited lessons learned welding armor onto Shermans in Normandy. Staff Sergeant Benjamin Norwood survived the war with 4 Purple Hearts and a Silver Star. His Sherman crossed the Ruhr, fought through the Ruhr pocket, and was finally knocked out by a Panzerfaust team near the Elbe River on April 14, 1945, less than a month before German surrender. The improvised armor that had protected him through 11 months of combat finally failed when a German soldier achieved a perfect shot into the turret ring from 10 meters. Norwood and 3 crew members escaped. His loader died instantly. Examining the wreckage afterward, Norwood counted 17 separate impact points on his tank's hull and turret, where various armor configurations had stopped rounds that should have penetrated. 16 times, the modifications had saved his crew. The 17th time, they hadn't been enough. The improvised Sherman armor modifications represented a unique moment in American military history when institutional failure created space for grassroots innovation. The Army had entered Normandy with tanks inadequate for the combat they faced, and rather than waiting for institutional solutions, soldiers had improvised their own. The modifications were unauthorized, often dangerous, sometimes ineffective, but they emerged from the fundamental principle that dying in inadequately protected tanks was unacceptable when solutions existed. The story challenged comfortable narratives about military innovation that it flowed from formal research programs, professional engineering, and institutional decision-making. In reality, some of the most effective improvements came from enlisted men with welding torches, scavenging scrap metal, and learning through trial and error what worked to keep them alive. The Army eventually sanctioned and improved upon these field modifications, but only after soldiers had demonstrated their effectiveness by violating regulations. Modern military organizations studying the Sherman armor modification phenomenon identify it as a case study in adaptive innovation under pressure. The modifications succeeded not because they represented technological breakthroughs, the principles of spaced armor were well understood, but because they emerged from practical experience and were implemented faster than institutional processes allowed. The soldiers doing the welding received immediate feedback on what worked. They survived or they didn't. This feedback loop drove rapid iteration and improvement impossible in formal development programs. The final irony was that improvised armor modifications continued even after factory packages became standard. Units receiving new Shermans with T-26 armor in late 1944 and early 1945 often added additional field modifications, believing that factory solutions didn't provide adequate protection for their specific tactical situations. Maintenance companies that had spent months developing armor modification expertise continued applying that knowledge, creating hybrid configurations, combining factory and field solutions. The Army never fully controlled the modification process. Soldiers continued innovating until the war ended. Corporal Culin's crude welds in June 1944 had started a movement that transformed how American armor fought in Northwest Europe. By war's end, virtually every Sherman in combat bore some form of additional protection, whether factory installed or field modified. The illegal armor trick that one welder had improvised to protect his friends had become standard practice across the entire theater. The men who'd violated regulations to weld steel onto their tanks had been right all along. Survival mattered more than compliance with engineering specifications that hadn't accounted for the reality of combat against German guns. The welders who'd worked through nights at improvised workshops, the tankers who'd scavenged steel from destroyed vehicles and bombed buildings, the maintenance officers who'd looked the other way while enlisted men violated regulations, all had contributed to innovations that saved hundreds of lives. Their legacy was written not in official reports or engineering journals, but in welded steel on thousands of Sherman tanks, and in the survival of crews who otherwise would have died in vehicles, their own army considered expendable in the pursuit of strategic mobility. In the end, that was the real story of the Sherman armor modifications. Not that soldiers had been clever or resourceful, but that they had refused to accept institutional failures as inevitable. When the army couldn't or wouldn't provide adequate protection, soldiers had provided it themselves. The welds were ugly, the modifications unauthorized, the whole program operating outside official channels. But it worked. And in war, working is the only standard that matters.